Dr. Valisoa Razanajatovo Misanantenaina is currently a postdoctoral researcher at Stellenbosch University in the Department of Logistics and holds a PhD in mathematics from the Department of Mathematical Sciences of the same university. She has always been fascinated with scientific areas from an early age, and after completing her bachelor's degree in mathematics at the University of Antananarivo, she joined the African Institute for Mathematical Sciences, where she did a master's in mathematical sciences. She then moved to Stellenbosch University to pursue her research in the field of graph theory. Today, she will be presenting with us on her work on the average size of independent sets and matchings in graphs. Please join me in welcoming and Valisoa, over to you.
Thank you so much, Diane, and thank you for a nice introduction. So today I will talk on the average size of independent sets and matchings in graphs. It is a joint work with Dr. Eric Angiantin and Prof. Stefan Wagner. The main motivation of this work was an article of Jamieson in 1983 when he characterized the average order of subtrees. And we were interested in looking at the average size of matchings and independent sets. So instead of subtrees, we considered matchings and independent sets. So let's start with some definitions. If you have a simple graph G, a subset A of a set of vertices is an independent set if no pair of vertices of A share a common edge. And we denote IGK, the number of independent sets of size A. So if you look at this graph, it's a simple graph. It's a star on 4 vertices. We can see that all the red vertices, any subset of the red vertices can form an independent set. But 2 vertices of different color cannot be an independent set since they share a common edge. And similarly for the subset A of the set of edges, it is called an independent edge set or matching if no pair of edges of A share a common vertex. And we denote MGK, the number of matchings of size K in G. If you look at this graph, this is a complete graph, so all the edges are there, and it has 4 vertices as well. The edges of same color form an independent a matching. So the red edges is a matching of size 2. The 2 red edges are matching of size 2. The 2 blue edges are matching of size 2, and the 2 black edges are matchings of size 2 as well. But if you form a set with edges of different color, then it cannot be a matching since they will share a common vertex. And note the size of a largest independent set is called the independence number, and the size of the largest matching is the matching number. So for our case here with the complete graph K4, we can see that the maximum we can have is 2 edges. Because if you add another edge, then it will be an edge of a different color, so it's not a matching anymore. So here, the matching number is 2. And now a formal definition of the average size of independent sets. So IG1 is the total number of independent sets in G. So why IG1 is, it comes from the matching polynomial. So independence polynomial, where we have IGK times x to the power k. But if you change x to 1, we have IG1, and we have the total number of independent sets in G. And then the second line is the total size of independent sets. And the average size of independent set will just be the ratio between the two. So in other terms, it's the logarithmic derivative of the independence polynomial evaluated at 1. And for ease of notation, we'll write IG instead of IG1 and TG instead of I'G1. And we do the same for matchings, where MG1 is the total number of matchings, M'G1 is the total size of the matchings, and the average size of matchings will be just the ratio between M' and M. And again, for ease of notation, we'll write MG instead of MG1, as well as SG instead of M'G1. So we'll just show you quickly few examples. So remember the first graph I show you, the star on 4 vertices. If we compute the average size of independent sets of S4, we know that there will be first the empty set. So it has size 0. So we have one empty set of size 0. All the 4 vertices are themselves an independent set. So one vertex is an independent set. So we have 4 of them. So 4 independent set of size 1. And then we have seen that the red vertices form an independent set as well, any subset of the red vertices. So if you take 2 of them, there will be 3 that can we form. So we have 3 independent sets of size 2. And the last one, if you take all the 3 vertices together, we have only 1 choice for that. So it is 1 independent set of size 3. And we divide everything with a number, total number of independent sets. And we have 13/9 then for the average size of independent sets of S4. And then if we compute the average size of matching of K4, the second figure we have seen today, again, we have the empty set, 1 empty set. We have all the ages. 1 age is a matching. So we have 6 of them. So 6 matchings of size 1. And then we have the 2 blues, 2 red, 2 black, which is 3 matchings of size 2. And we divide everything to the total number of matchings, and we got 12/10 or 1.2. So now let us move to some useful recursions on the IG, TG, and GSG. I want you to focus first on the first equation. So it says that the number of independent sets in G is equal to the number of independent set in G minus the vertex V plus the independent set in G minus the closed neighborhood of V. Closed neighborhood is just V and the adjacent vertices to V. And we can see from this equation 1 that if we remove a vertex from a graph, then it will definitely decrease the number of independent sets. And now if we move to the fourth equation, we can see that if we remove an age from the total number of matchings, then it will decrease the number of matchings. So we wanted something similar for the average size, but unfortunately, it's not true. So the average size of independent sets or the average size of matchings are not always a monotone function. So I will show you a counterexample now. So remember again our star graph S4. If we remove the leaf, one leaf from the S4, then we have a star S3. And the average size of the star sphere will be 1, which is less than the 13/9 we have computed. So it will decrease the average size of independent set. However, if we take out the blue vertex, like the center, if you take out that vertex, we'll end up with an ageless graph or empty graph of size 3, which will have an average size of independent set greater than the average size of S4. So there is no always decreasing or always increasing, but it is a mix. And now for the case of matchings, if we consider this graph T prime, if we remove the age E1 prime here, it will increase the average size of matchings. But if we remove instead the age E prime 2, it will decrease the average size of matchings of T prime. So we don't have the monotone function anymore. However, we proved that in a graph G, there is a specific vertex phi such that the removal of that vertex will definitely decrease the average size of independent sets. And I just want to point here that the case for ages is not working. So there is no specific age that will definitely decrease the average size of independent sets. We can think again as the first graph you have seen, the S4. If we remove one age there, everything will increase. And for the average size of matchings, if we remove one age, there exists an age E, such that the removal of that age will definitely decrease the average size of matchings in G. Now, we were as well interested in extremal results. So usually it's when we talk about the general graph, so just a graph with fixed order and then vertex graph G, we proved that the average size of independent sets of G is between the average size of a complete graph Kn and the average size of the empty graph En. And again, for the average size of matchings of G, it will be between the average size of matching of the empty graph En and the average size of matching of the complete graph Kn. Usually when we have such inequalities, there is always a side which is easier to prove. And in our case, all the lower bounds here are quite straightforward. So since in a complete graph Kn, the only independent set we can have is an independent set of size 1, so just one vertex, or an empty, the empty set. That's why we have n over n plus 1 here, and it is really the smallest we can have. And the same for the average size of matching of the empty graph, since there is no matching we can form except the empty set. And for the upper bounds, it was like more difficult, but we just use induction and some of the recursions I showed you, and we have the upper bounds. So as you can see here, we have explicit formula for average size of independent set of a complete graph. We have explicit formula for the average size of the empty graph. We have an explicit formula for average size of matchings of the empty graph, but we don't have the average size of matchings of a complete graph. So although there is no explicit formula of that average size of machine of complete graph, it can be expressed in terms of a number of machines in the complete graph. So we have this n choose 2, and this is the number of machines in kn minus 2 over number of machines in kn. And when n tends to infinity, the average size of machines of kn will tend to n over 2. Now, we moved to the class of trees. So trees are connected acyclic graphs, so there is no cycle. And for any n-vertex tree different from the star, we have the average size of independent sets of Sn is greater than average size of independent set of T, and average size of machines of Sn is less than average size of machine of T. So the first inequality is proved by induction, again on the order n of the trees, plus some of the recursions I showed you, and the fact that the star minimizes the number of independent sets among all n-vertex trees. And this fact comes from Prodinger and Tichy in 1982. Whereas the second inequality is much simpler, since the average size of machines in the star is n minus 1 over n. And it is really less than 1. And any over 3t on n vertices will have an average size of machine greater or equal to 1. And I want to specify here that it's not only for the trees, but for all connected graphs, that the star is the one to minimize the average size of machine. And we can use a similar argument with only one exception, that the C3 has an average size of machine less than 1, but it's still greater than the average size of machine of S3. And now let's move to the path side. So the first thing we wanted then is an explicit formula of the average size of independent sets of an n-vertex path. And we know that the number of independent sets of a path follows a Fibonacci recursion. It is as well proved by Prodinger and Tichy. And if we use that information, we can have a general formula, and then we had this formula for the average size of independent sets of a path. So we have a linear term, 5 minus square root of 5 over 10 times n, plus a constant, and some, let's say, extra term or error term, because this term, when n tends to infinity, it will definitely goes to 0. And for the average size of a machine, we use the fact that the line graph of a path on n vertices is again a path on n minus 1 vertices. So line graph is a graph. So you have a graph. If you want this line graph, you take the edges of that graph to be the vertices, and you draw an edge if the edges in the previous graph share a common vertex. And in that sense, the independent sets in, let's say, the old graph will be the machines in the line graph. And since we already have the average size of independent sets of Pn, the average size of matching of Pn will be just like it can be computed using the average size of Pn plus 1. And now, as I say to you, those comes from the fact that the extra term here tends to 0 when n goes to infinity. So the limit of the average size of independence of path minus the linear term is just the constant. And the greatest average size of path is for n equal to 2. And then for n different from 2, it will be n equal to 4. And it is quite similar for the average size of matching. So the average size of matching of the path minus the linear term is the constant in the second equation. And again, the minimum is for n equal to 2 and then different from 2 to be that one. So for use of notation, we just say A to be the 5 minus square root of 5 over 10. And Cn will be the average size of independent sets of path minus the linear term. And Tn is the average size of matchings of a path minus the linear term. And if we compute the values of Cn and Dn, you can definitely see that it will alternate and it will go to the constant we have seen in the equation. Now, we proved that for every tree T of order n that is not a path, we have the following inequalities. So the average size of independent sets of a tree will be greater than an plus b, where b is that term here, it's a constant here. And the average size of matching of T is less or equal to an plus b prime. B prime is this. And consequently, we'll have then that the path minimizes the value of average size of independent sets of T and maximizes the value of average size of matchings. So we prove this theorem, this inequality, by induction on the order n of the trees. So for n less or equal to 3, there is nothing to prove. The only trees we have are all paths, so 1 vertex, 2 vertex, or 3 vertices are just paths. So we assume that the number of vertices is then greater or equal to 4. And we consider as a vertex phi whose degree is at least 3. So that vertex must exist since T is not a path. And then we can denote the neighbors of phi by phi1, phi2, phi and the components of T minus phi. So we remove the vertex phi with phi, then we have T1, T2, Tk. So those are the components that contain phi1. T1 contains phi1, T2 contains phi2, and Tk contains pk. And if E is the age between phi and pk, T prime will be then the tree when we remove the component Tk. We have the following equation for the average size of independent set of T. You can use the recursions we had before to get to that. And if our K is greater or equal to 5, we can denote to rho the IT minus phi over IT and rho prime IT prime minus V over IT prime. And after various manipulations, we end up with the average size of independent set of T greater than AT plus B. That was for K greater or equal to 5, but for the cases where K is equal to 3 and K is equal to 4, we go back to equation 9 we have here, and we study different cases depending on how many of the branches will have 1, 2, or 3 vertices. And even with the 3 vertices, we have the choice, like, do we attach the center or do we attach one leaf? And this gives us a total of 35 cases for K equal to 3 and 70 cases for K equal to 4. But we checked all the cases and it satisfied our inequality. Now for matchings. So we come up again with the average size of matching of T. And it's quite long formula, but it's not that complicated to obtain. So we have number of matching T minus E over matching of T. And we have times A here. Remember, the T prime is the 3T where I removed the component TK. So that was the T prime. So we have A's average size of matching T prime plus average size of matching of TK. And B is this one plus summation for size of matching of TJ plus average size of matching of TK minus the VK. And again, we divide it into cases. So if K is greater or equal to 5, we prove the inequality using the fact that what happens if one of TJ is P2, then we have some bound, and if none of them is P2, we have another bound, but nonetheless, we prove that it is definitely less or equal to AN plus B prime. And for K equal to 4, just using that fact, we proved again inequality. And for K is equal to 3, we did the same thing as with independent sets. So we studied all the cases depending on how many vertices have the branches, and we had to check the 35 cases, and the inequality still holds. So then we moved to a general consideration. So we have evaluated our independence polynomial and matching polynomial at 1 to get the average size of independent sets and the average size of matchings. But now what will happen if it's not 1 anymore, but it's some just positive number alpha? So like we have the weighted independent set, which is IGK times alpha k, the sum over k. The first derivative evaluated at k, which is k times IGK alpha k as well. And then we took the average size, the weighted average size of G, which is just a ratio between the weighted number of independent subsets and the total size of independent subsets. And we do the same for the matching cases. And all the proofs we had, like for the complete graph, for the empty graph, for the star, all the proof can be adapted to this weighted version. So all the theorem we had can be extended for this weighted version, except for the path Pn. So for the path Pn, it works only when alpha is between 0 and 1. When alpha is not in 0 and 1, then we had some problems, since remember the extra term or error terms I showed you when we had the explicit formula for the path, it doesn't disappear anymore when alpha is greater than 1. And so we'll end this talk by asking a question. So if it is not the path, so let's check for a big alpha, what type of trees then minimizes the weighted average size of independent sets? And what type of trees maximizes the weighted average size of matchings in graphs? And thank you so much for your attention.
Valisoa, thank you on behalf of the Centre and of course on behalf of the audience. Thank you so much for a wonderful presentation. It's great to see your work. You know, some people might know you're one of our funded students, or you were. I think you still are. And so it's wonderful. And also, you know, as graph theory is one of our newest, or is our newest focus area, to get so much exposure, so much information on it is always wonderful. So thank you. And I'd like to now invite our audience to come forward with any questions or comments that they might have. I'm just going to check the chat in the meantime, but please, audience, as I said, just unmute your microphone and I'll be able to see you come forward. Thank you. Hi, Augustine Monagi from WITS, please go ahead.
Yeah, I just want to say that it was a wonderful talk and well presented, and personally I enjoyed it very much. Well done.
Thank you so much. Thank you.
Thank you so much, Augustine. Okay, if anyone else would like to come forward, just unmute your microphone. So Valisoa, as I often say, you know, sometimes people, once they've seen a seminar, they kind of need perhaps time to process and formulate their questions or comments. So with your permission, I'd like to ask if you're happy for, you know, if anyone thinks of any questions or comments after this, to email you.
Yes, yes.
Excellent,
Okay, no
thank
problem.
you. Wonderful. So we have included, as I said, we have included your email address in our poster. It's available on our website via our newsletter, as well as the event reminder that we sent out earlier this week. And alternatively, people can just email the Centre via our contact page. And I'll be happy to provide them with your details if you're happy with that. We've got obviously the new Privacy Act coming in. So I just want to get your consent for that. And I'll be more than happy to do that.
Yeah, okay, no problem at all.
Wonderful. So Valisoa, thank you so much again for presenting with us. It's been a pleasure to host you this morning. And thank you so much to our audience for joining us. And I wish you all a very good weekend. Thank you again.